Okay, we've been using stock and flow to understand the containerized cargo system. So what we want to start to look forward to now is as we plan to control or analyze that system in terms of analytics or management controls, we're going to need a data structure that tells us what's going on in terms of that system. So we're starting now to get a little bit past the system engineering side of the cargo management system and start to ask ourselves, what kind of management information system would we want around that system if we were going to try to control it? So typically we talk in terms of databases, but we don't want to get too technical here. I'm not interested in designing a database right now, but we do want to start to get into some of those data constructs as we go through. So in the database world, there are relational databases. Many people have heard of those, where everything is tables and relationships and columns. And a subset of that are dimensional data warehouses, which we tend to be reading about in our readings. So let's take a look at how the dimensions solution solves one of the bigger problems we have in the relational world. Designing relational databases for big complex data structures is just the number of tables, the sheer magnitude of the database becomes completely unmanageable as we see our way through. It's called relational exponential growth. The number of tables in a relational database grows exponentially as the complexity of our system goes up. So for anything other than a very trivial system, a relational database can be a real inhibitor to true management information capabilities around that. So let's take a look at the containerized cargo from that standpoint now and what we have going on. So we had 3 basic flows through a system that included 5 stocks in our overall system. So a lot of our management information capability around this system is going to be managed at the flow level. We'd want a data structure or a data warehouse or a database, whatever you want to call it. We want some kind of a data structure that will manage all of the data in our entire system. But for the sake of just this very brief little video, let's focus in on just the flows. The 3 basic flows coming through. I want to be able to store as much information as possible about what's going on with those 3 flows. And what we talk about here would extrapolate to include all the stocks and all the other dimensionality of my problem space as well. So let's just look at how we would do that. So I might want to build a one-dimensional structure where I just keep track of my vehicles and I want to know all the transactions related to the vehicles. So I can do that in 2 tables basically, is record all the vehicles and then just record transactions against the vehicle. That's a one-dimensional problem, and it only requires 2 tables to do that in a relational structure. But if I add to that a second dimension, containers, I'm going to need more tables because I have the container master and transactions about the container that I'm going to want to store. But I need more than 4 tables because I might also want to record information about when that container was associated with that vehicle. So the container vehicle mapping becomes master data in itself, and I record transactions against that. So I've grown from the 2 tables needed for just a one-dimensional problem to 6 tables needed to record a 2-dimensional problem. So if you're looking at the math, you can see where this is already going to go. So just vehicles and containers and their intersection requires 6 tables. If I now add to that a cargo view, I want to keep track of the cargo itself. I can know a shipment order on my master and record transactions against that. But I'll probably also want to know transactions that place that cargo in a given container. So my container cargo mapping is going to be important, or as well as the cargo related to a vehicle. Perhaps I need to have that mapping going on and have transactions against that. Or I might actually have situations where I want to record information transactions against the intersection of all 3. A transaction where this cargo was in this container while it was on this vehicle would go in that 3rd leg. So as I go to a 3-dimensional problem, my relational tables have grown to 15. So it's going to become very unmanageable very quickly. In fact, if we were working on a whiteboard for the same thing, when I teach this class in a live setting, this is what the whiteboard at the front of the classroom ends up looking like by the time we finish some of this discussion. It becomes very, very unmanageable as we see all these tables and relationships flowing all over the place. So for 1, 2, and 3 dimensions, the number of tables is fairly manageable, 2, 6, and 14. I can do a 3-dimensional problem space with 14 tables by the time I deal with all the intersections and things of that nature going on. But if I get beyond that now, the numbers are going to grow quickly because it turns out my numbers are growing exponentially. That 2 to the n minus 1 is driving that. That's the number of intersections and viewpoints that I could have. For a 25-dimensional model, it requires over 67 million relational tables to potentially implement the entire model. Now, do we actually implement databases with that many tables? No. What that means is if I pick, say, the top 1,000 tables, even the top 10,000 tables, and just define those in my database. What I'm saying is any of the MIS requirements that I have that would have required all those other tables are going to have to be done another way. I can't naturally evolve my stock and flow model into a database structure that will work as I go through. So it's simply not controllable as I go through. And as you'll see in a few minutes, most major problems have a lot more than 25 dimensions. My book on data warehousing is a 26-dimensional healthcare warehouse that involves hundreds of millions of tables in it, if you were to do just that. But the fact is, the number of dimensions is still underestimating dramatically the number of tables you might need as you go through. So let's take a look at some of those scenarios. But if I reduce, so instead of having a group of tables for each, if I design a single fact table that has the ability to store data against any of the dimensions. Sometimes the fact is only against one dimension, sometimes it's against all three. And we'll see in database technology how to do that. It's not that difficult. It is possible to eliminate the exponential growth by thinking in terms of dimensions of data that'll self-reference as they go through. So if a three-dimensional problem in a dimensional fact table construct with dimensions, a dimensional data warehouse, if you will, only requires basically 4 tables to do that. The number of dimensions, each requiring a table, plus 1. It's a little more complicated than that, you'll see when we get into the details. In fact, each dimension requires 6 relational tables, not just 1, but 6n is growing a lot slower than 2 to the n. So either way, you've eliminated the exponential problem as we go through it. My healthcare data warehouse with 26 dimensions and a fact table has fewer than 200 tables in it. No matter how much data I add to the structure over time, the number of tables will never grow. And that's what we want in this kind of structure, is a way to manage the data and meet any requirement. So again, I'm only showing what the warehouse would look like for these 3 dimensions. Our original model had more dimensions, routes and facilities and customers. So as we add more and more dimensions, we see more and more tables, but never more than n plus 1 as we go through. But now let's take a look within the dimension, because part of my functional architecture for a system is not only do I manage my flows, but I've got to be able to acquire, maintain, and retire them. I got to be able to think about and talk about the dimension in and of itself. A container can be dry or wet or gas or refrigerated. It might be a 20-foot or a 40-foot or a 45-foot container. There are properties or characteristics of the container that I'm going to want to keep track of as I go through. Now, they can be properties of the container table in my database, but I may want to store information about container types, not just about containers. So a rule that says you can't put a 40-foot container on a 20-foot truck might be an important rule to have in terms of what's going on. So I need to be able to reference this kind of data in terms of my management information structure, my data warehouse, as just the type, not necessarily the instance. So the way I do that typically is I define for my container dimension, I define a little hierarchy of tables, more than one table, what are called subdimensions, where I might store in my container dimension the actual instances of containers, and maybe I have hundreds of thousands of those, but also a subset of the dimension is simply all of the container types, the 20-foot drive, the 40-foot drive, things of that nature. So if I want to record a fact against just the type, not the instance, my fact can point to the container type row in the dimension. So I'm going to see type rows. Typing data is often needed within a dimensional structure for management information. I ask a lot of questions about things that are by type. My vehicles might do the same thing. I've got to manage my vehicles, only they're even more complicated. So the vehicles themselves could be trucks or trains or barges or vessels, but there's more detail needed to understand a vehicle, because a vehicle contains a unit. My truck unit contains a trailer, or multiple trailers. My train contains rail cars. My barges contain platforms. And my vessels have holes. So I've got to have 0 to n units associated with every vehicle and have a way to record that. So I might want to record a fact about the vehicle or about one of its units. Likewise, within a unit, I'm going to have slots, places where I can actually put my containers. Your typical rail car can hold 4 40-foot containers in it. So I've got a front and a back slot and an upper and a lower. So I got the upper front or the lower back, but I can indicate 4 slots within that rail car. So a vehicle that is a train has lots of rail cars, each of which have multiple slots. I'm going to want to keep track of that as I go through and properties associated with that. Some vehicles are powered slots and some are not. So where can I put a refrigerated container? So that's all data that I want to keep, but I don't want to keep this many tables as I go through. So I might define my vehicle dimension, again, as a mini hierarchy of vehicles, their units, and their slots, and put all of that data in the vehicle dimension. So as a subdimension, these are just different kinds of rows in the one table. I still only have a vehicle dimension table as I go through. Likewise, just like on the container, many things in a warehouse, I need to know the type. So I have typing data associated with that. Is it a truck? Okay, I need to know the vehicle type. How many of my vehicles are trucks? How many of my vehicles are vessels? Things of that nature. So I can have a vehicle type, unit type, and slot type. So anything I've got in a subdimension, it's almost by implication you should go ahead and think in terms of a typing construct for that. Because in a management information system, we're trying to aggregate data to answer management questions around planning and control, such that we often want to aggregate things by type. Show me all the containers that are on trucks. Show me all the containers that are on vessels. I'm often asking questions where I want to aggregate my answer up to a type. So always stick in the type as you go through. If I go back down to my generic model for my data warehouse where I had just the 3 dimensions, what this means is that some dimensions get busier than others. My vehicle dimension has lots of different types of rows in it, but a fact can point to any one of them. My container dimension has different kinds of rows in it, and my fact can point to any one of them. So as I'm developing my concept, my dimensionalization of a data warehouse, I'm not developing millions of tables, but I am potentially developing dozens, if not hundreds, of subdimensional constructs within my dimensions that I'm going to be able to store data for as I go through. And like I said, we always go with the typing construct. So it's possible that I would even add a type for my cargo, even if it hasn't come up yet, only because for every subdimension, it's common to need a type subdimension to go with it as I go through. Sometimes the business will have a name for one of the types. I'm inventing the name type just to make sure I get it into my model and don't miss it. But perhaps people in the industry will tell me that what I'm calling a cargo type is really the commodity code for what's in the cargo. So sometimes these subdimensions will have names that are relevant in the community that's doing it. If so, certainly go with that. But if not, stock and flow analysis will get us to the right place, even if we're not sure what to call things as we go through. So as my warehouse gets more and more complicated over time, I start to see that dimensionality growing, and I can start to build a dimensional warehouse that isn't going to have millions of tables in it, a full-scale cargo management data warehouse that deals with all of this different stocks and all the different subdimensions that go through. Will end up having 100 to 200 tables in it and no more. No matter how many billions of facts I store, no matter how many years of history I store, the database will always be able to store any fact I need it to have based only on those couple of hundred tables. And that's the key to dimensional data warehousing compared to relational database design. Relational database design tries to do something called normalization, making sure there's a column and a key for everything. But that implies millions of tables, and none of us are going to build that, particularly for an MIS solution on top of the operational systems that I put around this. This isn't a database for actually managing the day-to-day activity of cargo management. That's being done in operational IS systems. This is the data model, the data warehouse structure, if you will, for a management information system that sits on top of all of that. So I end up basically simplifying my diagram. I tend to draw the diagrams this way, where you indicate each dimension that you're going to have and which is the fact table. And that subdimensionality that started to grow, you end up putting as a list outside the box. You don't bother to list the typing entries. They're presumed that anytime you have a subdimension, you probably have a type. But the vehicles are not just vehicles, they're also units and slots. The cargo isn't just cargo, it's also commodities. So the list of subdimensions gets represented visually, but not exactly exhaustively as we go through the paradigm, seeing our way through. Having done that, we don't really need to explain that the upper boxes are dimensions and the bottom one is fact. So I throw away the word dimension. I throw away the word generic on fact, and I say a data warehouse has a series of dimensions, in this case vehicles, containers, and cargo, against which I can record facts. What you end up with is the dimensions end up looking a lot like your conceptual diagram back when you conceptualize the system. So you can predict that locations and facilities and routes are going to end up in this model as well as another variety of things. But again, the database size needed to do this is going to grow as a function of n, not as a function of 2 to the n. So you've eliminated the exponential problem. As I said, many major MIS systems need 20 to 30 dimensions, but still you're only talking a couple of hundred tables in a full-scale relational database to implement that. And that's certainly manageable with the generic architectures that are available today.